Kaz, can you go to next slide, please? So my name is Rufi Ran. I'm the project engineer from Integral, and my co-speakers are Kaz Brahmana, who is senior architect from Perkinson Well, and Maureen Sanchez from RDH Passive House Consultant. Three of us have been working quite closely in the past year to deliver the project of University of Victoria, the Students' Housing Project, and during which we have encountered quite a lot of challenges, and we have a lot of interesting stories we would like to share in the next 90 minutes. Next slide, please. For today's agenda, I think we'll start to talking about the project overview and aspiration, and then we will try to dive into some innovative design process and technologies which we have developed for the project. We will also try to explain how we use Passive House as a tool to influence and form the design decision makings. And the presentation will end with a summary of lessons learned and food for thought. Next slide. So now Kaz is going to start with explaining the project overview and aspirations.
So one thing I think is important to touch on here is sort of why Passive House and why it matters from an owner's perspective, which helped frame this whole project. So really quickly, the University of Victoria is sort of a medium-sized university on Vancouver Island. Here's just an aerial photo on the left, and on the right is a graphic of their existing district energy system that they already have. The university's big problem and why they turned to Passive House was summed up by this slide. On the left, we have their existing emissions profile, so about 91% from gas. And on the right, what we have is their emissions profile over time. So the black line is the historical emissions profile. The yellow or gold line is their projected emissions profile. And the green dotted line is the provincially mandated reductions in their greenhouse gas emissions. So it's obviously a big challenge for any institution. They're trying to grow their institution, grow their square footage, but they need to lower their greenhouse gas emissions profile. So that sort of framed the problem for us, and Passive House was seen as an appropriate vehicle to begin tackling this problem. You can see by 2030 is really their initial target. They have a significant emissions gap per year. So the general strategy we'll talk about today, the idea is simple. It's basically reduce your need for electricity, recover where you can from any heat source, and then electrify in BC. Well, we'll touch on that. Electrify for this project what remains.
Before diving straight into Passive House target, we wanted to have a quick chat on the carbon side of things, because everybody is familiar with the fact that you only have a certain amount, your EUI, right, your total energy use intensity, which is the metered energy, but you obviously need way more at the power station because of all the losses that you have throughout the process. And that changes as well with the carbon intensity, with the energy source that you have and the carbon intensity associated with your energy source. So we're all familiar with that idea. However, when we start looking at Passive House, we don't necessarily see the word carbon, right? Kaz, one more press. And we still have that same idea in that primary energy renewable target, which might not always be clear to people, but actually is a mix between two different measures, one still being the total energy use intensity that you have in your building, but the second being that what is your carbon or energy cost based on which energy source you're working with. So that primary energy renewable target, which is the second target for Passive House certification, does englobe both of them together. So it's not because we don't see the word carbon that Passive House doesn't fully care about it. So Now, looking at that idea, we need to zoom in a little bit and start realizing that you know, where the project is located has some impact. Next. Thank you. And what you're seeing here is the carbon intensity of the electricity grid in Canada. So I'm sure you're all familiar with this, but I think it's worth pointing out the difference in factors that we can see where roughly, you know, BC is already at a good start, not the best, but really good at 12.9 grams of CO2 per kilowatt hour. And you can see that Alberta is roughly 60 times higher than that, which really changes the context. Whereas for some of us, including me, working on the east side, Ontario is about 40, which is still 3 times higher than BC, and Quebec is leading the way with like 1/10 of what BC. Of the carbon intensity of the electricity grid in BC. So it is definitely important to look at the overall picture and then zoom in into where our building is located. So zooming in a bit more, what does it look like for BC? Well, we've already seen the greenhouse gas emissions through the previous slides, where you can see the huge discrepancy on the right between the greenhouse gas emissions associated both with the gas and electricity sources. And then the paradox is that the cost is the opposite way, which is not always helpful to make the right decisions. So Kaz and Rufi will touch a little bit more on that later on in the project.
Sorry, so just to step back a little bit, not assuming everyone is familiar with the project, we'll just walk through kind of what the project is, where it sits, what's comprised of, to give everyone a sense of really what we're talking about here. So zooming in, we saw sort of the aerial photo of UVic before. Here it is just from the top. It's defined by the ring road. The academic precinct lives within the heart of the ring road, and their housing precinct is just to the east, identified here by the dashed line. We have a large amount of programs, about 330,000 square feet, and it's split across 2 buildings here to help push forward some of the urban and campus objectives that UVic has in place. The siting was largely driven by the existing campus greenway, which currently runs through the heart of the ring road. It's really high value public thoroughfare, but really peters out at Ring Road. So this siting gave us the opportunity to drive that across Ring Road to better connect the campus and revamp their campus greenway, and also provide a north-south greenway as a new spine within the housing precinct, which will help them organize future renewal and development. At present, a lot of the housing on campus has been developed over time. You can just see from the photo here, there's a lot of townhouse development when they had the Commonwealth Games, and then they've just sort of piecemealed together as they've had access to funding, and this will help give them a overall master plan framework. I should quickly note, just on this one, sorry, that we are deconstructing 3 buildings, 2 existing residences that are aging and in need of a large amount of repair, and their existing dining hall. So with those 3 buildings coming down, and we're adding about just over 620 student beds, but we'll have a lower carbon footprint overall. So that's just, I think, a really compelling part of this project. They actually get to grow their campus, but have a lower greenhouse gas emission profile. So what's in these 2 buildings? This is site 1 on the left and site 2, we're calling it on the right. So they're from level 3 up, they're both student housing. Site 1 is 8 stories or 6 stories of student housing on a 2-story podium. The second site is 9 stories on a 2-story podium. In site 1, we have, and there's a mix of program in the podium spaces, which sort of adds the complexity. The student housing part isn't the hard part, really. But in site 1, we have a commercial kitchen that's serving about 9,700 meals a day. An important note here is that no one's really attempted to certify a kitchen of this scale before, and we'll get into that more later on, but it's an interesting component of this. We have an 800-seat dining hall identified in green, kind of wrapping around the servery and the kitchen. Then in site 2, we have a banquet hall seating about 500 people and 2 large academic lecture theaters on the lower floor. So it's quite a complex mixed use program. So how do you start that? That was sort of, we were worked quite closely with RDH on this and Integral, the whole team, to figure out how do we start to eat this thing in bites. So the tower area on site 1 specifically, which is the more challenging site with the commercial kitchen and the high energy use, we have about 59% of the floor area is the student housing portion. So we split that into one PHPP model, and then the more complex Podium became a separate PHPP model. So we're kind of working with 2 problems, one a little easier than the other, and taking a blended approach overall. So just to start off, to set some targets and begin us down a path, and we'll get into all of this stuff in more detail. We knew that the podium, or the public spaces, would want more glazing, they would require more energy use, and we knew we could be relatively aggressive in the student housing portions, being that it's a typology that has been certified a number of times across the world. So we set our space heating demand targets at 8, so trying to almost cut in half the passive house target for the student housing, and then about 25. So have a little more generosity, allow more glazing, these kinds of things in the dining hall in those areas, getting a blended ratio of 15, so hitting the passive house targets overall. So one of the things we knew we would be a struggle, or could be a struggle through the design process, was the idea of having a strict glazing budget. These are very public buildings. They want to be transparent in a number of places. And one of the concerns really we had with Passive House and client size off the get-go was the idea of a windowless box. I think that still exists when you see some photos of old Passive House projects. It's not the glass box that people may want to see or think of in modern architecture. So what we did here was really thought about our glass ratio as a budget, and tried to spend that very generously in high value areas and migrate all of the public program to where the glass is, or vice versa, co-locate those things. So here in orange are really the public areas, the student lounges up the tower, and then the podium spaces. So you can see that's really where we tried to spend our glazing budget. Also the form of the building, we tried to naturally overhang some areas we knew would be very heavily glazed to avoid the penalty of having to introduce glazing or shading there as well. So after we went through all these exercises and right-sized all of the glazing to the project, went through the spaces, sort of saw what they needed, and tried to be generous where it made sense. Our original targets were about a 30% window wall ratio, 30% window through the student housing portions, the upper floors, and about 50-50 was the target down low. So generally we recommend a reasonable starting point for high efficiency buildings, about 40% glazing for a residential typology. That'd be sort of the ballpark. And here, when we went through the design exercise, just due to the typology, we ended up with 16% glazing through the tower portion, which is actually a lot less than we anticipated, and only 25% in the podium. And I'll just walk through what that means. That feels really low, but here's a view, a rendering from the interior of the dining hall in the first site, looking south toward the public green space. So you can see here we've complete walls of glazing, both upstairs and downstairs, trying to create as much transparency between the new public realm and these public spaces in the building as possible, trying to open these up. And it just means we are more conservative with glazing where it isn't required. So I think the take home here is you can still have amazing spaces, amazing urban realm, and amazing transparency, but hit really high efficiency targets. I mean, it is all triple glazed, thermally broken curtain wall. Just FYI. So here's another view looking at it from the southwest. We have the prow of the building kind of overhanging on the second floor, creates a 3-season covered dining space. Victoria does get a lot of rain, so we can try and blend that indoor-outdoor space. And there's a multi-purpose room above, really, with floor-to-ceiling glazing, inviting that. And you can see the glass along the ground floor and the new campus greenway that'll be running east-west to the campus. And then on the upper floors, we have a textured facade. There's a company in Victoria which does custom metal cladding, which we were able to leverage. You see here the student lounges running up the tower as well, offering a complete wall of glazing, quite generously glazed. And here's just stepping back, looking at both buildings together, framing what'll be the new heart of the residence precinct, this new urban quad framed by these 2 new buildings, flanked by public program on both sides. So that's a little bit of the background, sort of what we're looking at. And then for how we sort of started under the hood, I'll let Maureen walk through that.
Thank you, Kaz. So yeah, as Kaz mentioned, we started with a couple of SD PHPP models, so PHPP being the software for Passive House certification. And we started with these SD models with rough targets, but in no way is Passive House prescriptive, right, as we know it. So more or less, we got into a big game of turning knobs and pulling levers until we found the perfect combination. That's what we were after. So combination of what, you ask? To maintain a comfortable environment, for the building to stay comfortable, we need all the heat losses to match with the heat gains. You know, losses, we have windows, walls, roof, floor, thermal bridging, ventilation, infiltration, and then you have the solar gains and the internal heat gains on the other side. So this is all good, but most of the time in our heating dominated climate, the gains are not enough to balance the losses. So we need to add heating to keep that delicate balance. So the amount of heating we're adding and we're allowed with Passive House certification is about 15 kilowatt hour per square meter per year. So it's a very simple and set target. However, it is like you cannot just ask for a building with less than 15 kilowatt hour per square meter per year heating demand. You have to find that whole balance, because achieving that result is really depending on a lot of plates that you're juggling in the air. So in itself, it's already a delicate exercise to do this on one building at a time. Now, knowing that we were working with both the podium and the tower, our balance became even more complicated. Yes, I'll let you pass. So we were more or less playing with that balance on two sets at a time, right? On two portions of a building, and then trying to find that combined average of less than 15. So this is the slide that you'll recognize already. And what you're looking at is the PHPP result of the podium model on the right and the residential in the middle, which are then combined together on the left with the yellow tab. So really quite a delicate balance exercise, especially on a building of this size. So having that starting point, as I said, we started to touch a little bit like every plate, every box, every heat loss and heat gains, to trying to understand what would make the model sway a lot and what would barely make the model sway. And this is where the fun really started, with all the graphs everywhere and trying to move literally 15,000 things at the same time and saying, okay, what did I learn today? And what you're seeing is that out of all the sensitivity analysis that we did, the big levers were not necessarily the one we were thinking about. What we found were a few more than these three graphs, but we'll start with that. You're looking on the left at the external wall insulation thickness with and without insulation in the backup wall. And you can see that this is moving our tower between a range of 7 to 17 kilowatt hour per square meter per year for the heating demand. Quick reminder, we were trying to stay around 8, so quite a big swing. And then for the podium, where we were trying to stay around 25, you can see that the kitchen, so we have a big kitchen, we'll dive into this, but spoiler alert, we do have a makeup air and an extract, and the running time, the profile of that ventilation system made us have a really big swing, roughly between 25 and 40. So 25, we're all good, we're still passing. 40, we're like, I can't see certification anymore. Guys, can we do something? So that was another big one that swayed the model quite a lot. And the final one was the internal heat gains. So funnily enough, as Kaz mentioned, the residential part was really the easy part because we know how it behaves. It's a standard archetype, especially for Passive House. And so we do have a lot of default input data that we can rely on. Now, moving on to the podium, we've never looked at, you know, such a big dining space with a commercial kitchen, you know, throwing out that many meals a day. And we, at the very beginning, we had a lack of understanding of what it meant in terms of internal heat gains, because internal heat gains do provide free heating in the winter season, right? So you don't have to use as much of your energy budget for heating. And what you could see is that this one was a really, really big one, because our space heating demand was moving between 12 and 55. So again, 12, we're under 25, we're easy peasy. 55, we're like, okay, guys, this is not working. So extracting these key levers and then going on with it, like going in with the team to say, guys, everything else doesn't matter until we understand these things better. We don't really know where we are. So that was like a really big amount of work that was done, you know, towards the middle of DD for everybody to start diving into the next level. Funnily enough, a final few sensitivities that we did that we thought would have a bigger impact and ended up giving us really flat curves when we plugged them in was some roof insulation thickness. The same thing with the floor, a few items being changed on the windows, such as the glazing performance. All of these were tried, and for sure, they did have an impact on the models, but they gave us really, really flat lines compared to what you're seeing on the screen, which told us at least, you know, again, on such a big project, having so much to do, to say, this is what we've got to do right now for us to get a more accurate model and then make sure we can still reach certification. So that was a lot of work on all these levers to get to what are the choices I should make to maintain my space heating demand criteria, which is the first criteria. Now, it'd be too easy if that was the only criteria we were struggling with, right? So we move on to the next criteria for passive house, the primary energy renewable, PER. And what you can see is that the typical PER target is set at 60 kilowatt hour per square meter per year. But in our case, we are dealing with buildings that have a much higher density of occupancy than typical buildings. And we also are dealing with end uses that are terribly energy intensive, such as the kitchen. So luckily enough, we found a way to use or to obtain additional allowance for the PER target. And we played it in two different ways. We looked at the tower first in that pink color. And after more or less being in deep discussion and negotiation with PHI over the last 2 to 3 years on large buildings, and repeatedly, you know, time after time, finding that these large buildings could not fit within the allowance that was given, that 60 kilowatt hour per square meter per year, they created a tool to say, okay, we do recognize that depending on your occupancy and the size and the number of occupants in your building, you should be allowed to have a little bit more. So we use the tool to get to an extra allowance on top of the 60. For the podium, we also managed to get an extra allowance, but on a different basis. That time, trying to be fair and trying to look at a metric that, again, would be fair against other buildings, we're not talking in square meters anymore. We're talking in how many meals are we delivering every day and how much energy is required per meal. So we'll see with the kitchen section, the dive we went into to get to that energy per meal approach and additional allowance. Giving you a quick snapshot on the tower, you can see that we did have a little bit of an issue to start with. So this is the split per energy, per end use. So you see heating, cooling, domestic hot water, and household with a different degree of granularity plugged against the 60 kilowatt hour per square meter per year PR limit that we had. And you can see that we're miles past that. So we were all scratching our heads a little bit saying, I do not really see how much better we can get to get back in line. And now, using the new tool that is available from PHI at the moment only through certifiers, we plugged all of that in and had a big sigh of relief. I think we had probably a little happy dance with the design team to say, hey guys, with the type of building we're talking about and the number of occupants, this is what we're looking at. We're looking at a PHI PR allowance from 100 to 115 roughly, which is being refined as the design progresses. So we can see that the density does have a play into the total amount of energy your building is going to use, as well as your PER target. And using that tool definitely saved us in terms of what was allowed, and for us to have a bit more breathing space back into the design, because this helped us inform the decisions that we had to make later on.
Oh, sorry, Rufi, I think you're muted.
Sorry. So thanks, Maureen. And as mentioned by Kaz and Maureen previously, the project, we're working very hard in order to meet passive house onerous space heating demand and primary energy targets. However, passive house requirements is not the only focus throughout the whole design process. And the design team and the client have given quite a lot of considerations to future climate change, like how to make the building resilient enough towards the future climate change. Because we know passive house encourage the building to have a very robust envelope to minimize the unnecessary heat loss. However, if you, without clever planning, you may also lead to overheating risk by trapping all the internal heat gain inside the building facade. I guess like just trying to give everyone a little bit of my background. I worked 12 years in UK before moving to Canada. And in UK, usually at the beginning of the project, we always undertake two analyses. One is the overheating modeling, and the other is the PHPP modeling. Sorry, Kaz. The two publications you saw on the right side is the two guidance published by SIPSI, which is equivalent to ASHRAE in UK. These two documents help the designers to define the thermal comfort and then to assess the overheating risk. So for UVEC, so how can we make the project of UVEC to be climate resilient? Next slide, please. So luckily, our client, the University of Victoria, is home to the Pacific Climate Impact Institution, which provides information on the physical impact of climate change in the Pacific region. At the beginning of the project, they have shared their projected data for Victoria in 2050 and in 2080, which is the slide you now see in front of you. So there's the four weather data files, which you can see. The dark blue one, which represents the current weather file adopted by the code. And the second emerald bar represents the Abbotsford weather file. And the reason why we use Abbotsford weather file is because it is located at the same latitude as Victoria, but it has a very hotter and a dry summer. So before we received information from the Institute, we tried to use Abbotsford to mimic the future weather file of Victoria. But as you can see from the chart, actually what we thought as the future weather file are quite different as the weather data predicted by the institution, which are on average about 5 to 10 degrees higher than what we thought will be the future weather file. So obviously that will have a big impact in terms assessing the thermal comfort for the future. Next slide, please. So with all these weather data in hand, we then try to test some preliminary option. And the intent is trying to minimize adding extra services to the original design, but also be able to enhance the building resilient enough towards climate change. So what we have considered at the beginning are 4 options. Option 1 is to use passive cooling through natural ventilation strategies. Option 2 is trying to temper the ventilation air at a minimum ventilation rate to comply with passive house standard and to the code requirements. Option 3 is similar to option 2, but is to increase the ventilation rate and hence to increase its cooling capacity. And the last option is trying to use full mechanical cooling system. Next slide. So this slide basically is to summarize the comparison of the 4 options against 3 matrices. The matrix we have explored is first trying to test each option, their ability to maintain thermal comfort under current and future weather file. And the second matrix is to look at the impact on the overall energy consumption, such as the energy use intensity and space heating demand. And the last one, obviously, we cannot not think about the cost associated with each option. So as you can see, natural ventilation is always the most cost-effective and solution to deliver the ventilation, which also consumes the least energy. And to temper the ventilation air, like to supply the ventilation air at 14 degrees or 16 degrees, will enhance the building resilience towards the future climate. And however, I guess like the more ventilation air you deliver, the more resilience you will get for the building towards the future climate. However, it is at the expense of adding more energy consumptions and also adding more cost to the overall project. If we go completely to mechanical cooling system, it will guarantee to give you the full resilience towards climate change under the future weather file, like 2050 or even 2080. However, it is a very expensive options, and it also like has a significant impact on the TEDI and the TEUI. So after assessing the overall impact, this is the diagram which we're trying to demonstrate the final strategy we have incorporated into dome portion of the building. And so what we adopted is a hybrid ventilation. For the dome portion, we actually rely quite heavily on the natural ventilation. So by incorporating manual openable windows with quite a lot of openable areas, we also trying to introduce window review, which will act as solar shading to reduce the solar gain into the space. And we trying to incorporate thermal mass, like the exposed concrete surface, which will then modulate the internal temperature. So all this methodology will help to encourage users to use natural ventilation and to maintain thermal comfort. However, in addition to the natural ventilation, we also incorporate mechanical ventilation, which is fed from a centralized heat recovery unit, which also has the ability to cool incoming air to lower temperatures through the DX coil it's built in. Next slide. So after we did the design, we then tested again using task modeling methodology against under the 4 weather file, which I have explained previously. And we presented the results, which is the slide you see now, to the client and the design team. So throughout the whole discussion, we reached agreement that the mechanical system will be designed to address 2050 weather file. And the reason is because first, in order to meet the 2080 weather file, the current design has to be changed quite dramatically. We had to double the free area for the windows, and we also had to double the ventilation rates fed from the heat recovery units. So all these will have like quite significant impact on the the shaft size and also the space planning. And also for 2080, it's a bit further in terms of predicting the future weather file for the future. So there's a lot of uncertainties for the 2080. And also by that time, all the mechanical equipment probably will already be replaced as they reach their life expectancy. So considering all these elements, the design team has agreed to just address the mechanical equipment to 2050 weather file to maintain the thermal comfort. Next slide. So what I explained before is the strategy for the domes in the tower portion. So for the podium, which is level 1 and level 2, the strategy has been quite different because as Kaz mentioned previously, the level 1 and level 2 actually trying to incorporate a lot of glazing into the space in order to create this transparency from the internal space to the external environment. And also the space has a lot of high occupancy, so the focus has tried to be minimizing the cooling. But obviously we need to balance with the requirements of space heating demand as defined by passive house. So we work quite closely with Marine and Kaz, and did a lot of thermal modeling from Grasshopper to task modeling, and in order trying to optimize the solar shading to the podium level. Second one. And next, Kaz. We also, in order to avoid over-design the solar shading or the openable area, we also, like Kaz team, also like working really hard to dig into the historical sales data of the dining area, because in order to anticipate a quite accurate occupancy profile throughout whole year or throughout the whole day, because like people generate heat, and if you have a quite packed density of people, then you will need more cooling and will impact on your thermal comfort. So the profile, the occupancy profile plays a quite important role in terms of determining thermal comfort in the podium space. Next one. So this is the profile you can see Kaz team has derived from the historical sales data, and it has a dip during the summer period, which helps obviously the overheating scenarios during summer. I think Marine, you want to add from a passive house point of view?
Yeah, so that was a really big exercise that the Perkins & Will team did on existing sales data to translate it to the building we were working with, which then got into a very high level of granularity that was used by Integral to plug into their own overheating dynamic models, and then got further translated into PHPP input data, because as we mentioned before, the Podium is an archetype that we've never worked with. So we have no basis, no default input data. So when we were looking at the key levers, right, that we mentioned before, it was really important for us to have a good understanding of the occupancy that we have in this space, which also has an impact on the internal heat gain, as Rufi mentioned, right? Because people are, little heat source that we're trying to use in order to spend a little bit less on the heating. So that was a key item of modeling dragged throughout all the disciplines.
Next, Kaz. So this is a beautiful image created by Perkins & Will, and it basically shows the view from inside of multipurpose room, which is located at level 2 facing south and west. So you can see to your left side, basically is the west orientation, which the facade is fully glazed and it's heavily solar shaded. And the reason is because we need to block the low angle sun from the west during summer to avoid overheating. However, we still increase the density, the gap between the shading devices at the lower part, let's say trying to help introduce more solar gain during winter, which will help reduce the overall space heating demand. Well, to your front, which is basically facing south, and you can see the only part of the facade being solar shaded is the up part, which then blocked the high angle solar gain in the summer and allow the transparency to the lower part and also introduce solar gain during the winter to reduce the space heating demand. So that's the shading strategies for the multi-purpose room, and which helps to reduce the cooling load. Next one. So in addition to the solar shading, we also think about use mixed mode ventilation. And so all the, for the dining area and the multi-purpose room, and the high level of, we have incorporated high level automatic windows, which link to a temperature sensor. So whenever the external environment allows, the automatic window will open and encourage natural ventilation throughout the space. Next. So let's say trying to demonstrate the strategies throughout the whole year. So during peak summer period, when outdoor temperature is higher than indoor temperature, the spaces will close the window and initiate the full mechanical cooling system, which will be delivered through the tempered air from HRV units in conjunction with fan coil units. So that will give you the full thermal comfort during peak summer period. And during the shoulder season, and when the external environment is okay, when we don't have forest fire, then we will encourage to use natural ventilation. The automatic window will open in conjunction with mechanical ventilation from the heat recovery units to enhance the airflow throughout the space and trying to dissipate any heat generated from the internal people, lighting, and the equipment gain. Next one. So this image is quite powerful, which shows like compared to if you just use mechanical cooling only throughout the whole year, it actually, and if you adopt a mixed mode ventilation strategy, and actually the mixed mode, which is a combination of natural ventilation and mechanical cooling, then you actually reduce the annual cooling demand by almost 80% compared to if you just use full mechanical cooling throughout the whole year. And this is actually quite key in order for us to achieve the onerous passive house primary energy requirements. Next one.
Well as the space cooling demand, which people don't mention as well because we're in a heating dominated climate, but that work from Integral giving us results that like this graph was like, okay, we're good.
Thanks.
Okay, so moving on and taking a deep dive into kitchen. So how to plan for a low carbon kitchen. So that was fun, that was new, that was totally uncharted territory, as Kaz and Rufi can attest. So what is that new challenge? We have been given a set amount of energy, right? What we mentioned as that energy budget, both on the space heating demand, space cooling demand, as well as the PER side of things. So we're working really, really hard to make it fit into a really tight budget allowance, to get told that we have a kitchen that is trying to serve 8,700 meals a day. And this is where I scratch my head saying, okay, no, this is not working. This is not going to work. So bringing a kitchen that size into passive house levels is something that has never been done before. So there's been a lot of work being done internally within the design team, as well as a lot of back and forth with PHI, trying to support us in that new exercise, trying to figure it out. Giving you a bit of reference, when we've done a little bit of literature review, we've seen that it takes an average, let's say about 4.5 kilowatt hour of energy of final, right, metered energy per meal. And throughout the whole process of figuring out what was happening with our kitchen and where we wanted to go, after a lot of negotiations and a lot of, I guess I'm going to say, sandwich counting from Kaz and their teams, PHI gave us the allowance of 1 kilowatt hour per hot meal. So you can see that already we're talking about a factor of 4, like cutting the energy consumption by 4, if not further, when we start touching on cold meals and other things. So you can see that we had quite a challenge on our hands. So where do we start? Funnily enough, there's actually a lot of things that are free to help us get to where we want to be. And what these measures are literally good planning, but you need to know what you're looking for to get to that good planning. So where are we starting with? We're starting with, well, the kitchen uses a lot of energy, and where does it use energy? The first culprit is actually the ventilation system, right? We're cooking a lot, therefore we need to exhaust a lot, therefore we need to bring a lot of cold air in, and that amount of cold air that we have to heat is the biggest culprit. So if we're trying to get less ventilation while still maintaining good standard in the kitchen, right? We're not talking about cutting services, or like cutting the quality of the space. If we want less ventilation, we start with, how about products that produce less heat? Okay, well, that's a whole bunch of equipment that we change from gas or electric to induction based equipment. The next thing is that you need to ventilate in an effective way. So number 2 says that if you have wall-mounted hoods that have side guards as well, you're actually surrounded on 3 parts, which means that you need a lot less energy and a lot less ventilation to get to where you want to be compared to any island station. So that was then the next discussion back and forth with the university to say, I know these are really cool, but this is like going the other way where we're trying to do. So what can we do to still give the student the right student experience while not stabbing ourselves in the back in terms of energy? The third thing that we learned as well is that there are whole rows of kitchen equipment, and putting the equipment with the highest demand in the middle surrounded by others means that overall you need to ask for less ventilation to get to the amount of exhaust you want to get. And the final one, again, which is more common sense, is grouping appliances that have similar schedules, right? So that when the fan, like when the exhaust hoods are on, they're on only in one location where they need to be rather than different locations when it wasn't needed. So that was a lot of common sense, but still a lot of back and forth with the university and the kitchen staff to get to that.
As Marie mentioned before, throughout very careful kitchen planning and also through very careful selection of the kitchen equipment, it really helped to reduce the overall requirements for the kitchen exhaust flow rates. However, as Kaz mentioned, like this is a commercial kitchen which serves about 9,700 meals per day for the entire campus. So we still end up with approximate 10 cubic meter exhaust flow rates, which means like you need about 9 cubic per second makeup air. And you can see on the right of your slide, and Machine mentioned before at the beginning, we did a lot of sensitivity study. And if you turn the knob for the makeup air towards the higher end, then will have a really big impact on your overall space heating demand. So how can we to reduce the kitchen exhaust flow rate further? We have looked at a lot of measures. Can you press the button? Thanks. So we have looked at a lot of measures, as Marie mentioned, we're trying to avoid island ventilation, and we're trying to use all electric equipment. But on top of that, we actually look at using on-demand control ventilation system for the kitchen ventilation design. So what does that mean? It means basically for each kitchen exhaust hood, you have an automatic balancing damper. That links to the infrared sensor, which basically sends how much heat generated from the cooking station. And then they will send a signal to the automatic balancing damper, which then will change its position and then will change the speed of the fan to decide how much exhaust flow rates needed in correspondence to the amount of heat generated through different cooking activities. So that will reduce the overall exhaust flow rates. And also each kitchen hood actually incorporated a capture jet technologies. Don't scare by the name, but it is basically a fan built into the exhaust hood, which then creates an air barrier to the front of your hood. And what it does is it creates an air barrier so you can basically avoid the escape of the thermal plume generated from cooking stations. And in this way, it's more efficient to capture the heat throughout the hood. And in this way, you also, reduce the kitchen exhaust flow rate further. And after that, what we have done is trying to use a run-around coil, which basically trying to utilize the heat from the high temperature kitchen exhaust and then transfer that heat to the incoming cold makeup air. And in this way, we then reduce further on the space heating demand requirements. Next. So through all the technologies which I just explained, and plus Marine's careful kitchen planning and the selection of kitchen equipment, as you can see, the overall reduction is really significant. From the beginning of the baseline PHPP model, we managed to reduce the overall space heating demand by almost 82%. Next.
So yeah, as Rufi presented, that was a lot of work to tackle the first culprit on the kitchen, that was the ventilation linked to all the activities that we have in the kitchen. So a lot of work, but after careful planning and all these measures, we got to a point where the model was working again on regarding the space heating demand, because ventilation is one of your losses into your balance exercise that impacts your space heating demand. However, the ventilation was not the only thing in the kitchen that was breaking our models. So what is next? The next item in the kitchen are the equipment themselves and the energy consumption associated with them. So remembering back at the beginning of the presentation that we said that the PER does include that notion of carbon intensity behind it. The first step was for, again, the entire design team to go back to the university and the kitchen staff to say, can we switch from gas-based to electricity-based equipment, right? And what you can see is that we started the design, like that was like, what, 2 years ago or something? We started with 25 big gas-based equipment. And throughout that design process of going at it with a comb, like probably 2,000 times, if you ask the kitchen consultant, we ended up reducing everything to 3 equipment, and then down to 1 with like new equipments appearing in the market as our design progress. So that was a really huge thing, which from 25 to 1 gas-fed appliance, we actually obtained 83% reduction in greenhouse gas emissions, which is, absolutely key. Looking back.
I was just going to add one thing to this one, because there's an interesting point going through this exercise, because when we began this process, just from a client management perspective, the from the food service perspective, the food service operations at UVic, from their perspective, cooking with gas was the gold standard. That's where we started. That's what we wanted, and there was no one telling them otherwise. So we started to bring forward ideas of electric and induction. And then it was a long process of really introducing them to these products, sending them on product tours. They did engage the process. One thing that's really interesting to this process too is as there was a bit of reluctance from some parties earlier on, but as they started to announce their intentions toward Passive House and they started to see how the world around them became interested in the project because of that, you could see the user groups become excited and really start to lean into it. And then people like the food services and the chef really got on board with, working really hard with our team and the food service consultants to make this happen. So I just don't want to have people think it's just that easy. We suggested it and everyone was like, great, let's go all electric. At first they were like, no, electric doesn't work. It can't work for our use. Like it doesn't heat up fast enough. It's not reliable enough. But when you really get into it and you see the new products, particularly tending toward induction, it's just the way this market's going. So thanks.
Yeah, no, because so you had a red point. We were really lucky to have an engaged client throughout the process, and that was absolutely needed. Again, next slide, which brings the same point as well. So first of all, we were looking at a very completely uncharted territory, trying to figure out what was going on and how we could make it better and how we could even making it fit into the really, really small allowance that we were given by PHI. And to get to that, rather than looking only at a quantitative approach, which is typically what Passive House does, right? Calculations, we actually looked at both a qualitative and a quantitative approach. So what does this mean? The qualitative one was to say, look, we don't really have a lot of monitored data, but we do have common sense and we know what works and we get a sense of what will be useful. So let's go for a full checklist to make sure that we've done the best we can without any calculations. And this is where you can see on the pictures, touring supermarkets in Austria, we had a whole list such as display coolers will need to have a door. There's no open display coolers. Your walk-in freezers and coolers will have to have the thickest insulation in their walls that you can get from the market. Working on compressor systems rather than separating all of them, which means that you could not have a full, you could not recover the waste heat. Trying to plug as much as we could on one system so that we could finally get a heat exchanger and get some heat out of that. So a list of whole sets of systems. So that was one approach done with the design team. While in parallel, we again went through that excruciating exercise of going through the kitchen equipment line by line, trying to understand what are the running hours, what are they using in different modes between off to standby to full on. And that would not have been possible if we didn't have first the entire design team switched on, including the kitchen consultant that did so much back and forth, as well as an engaged client side. So that was really, really key. But what did it lead to? It led to a lot of deeper understanding and us finding a way to fit within where we wanted to be. We did a rough first calculation when we started diving into the line by line equipment list, and we're like, oh, okay, it seems we're at one on the electrical, the kitchen equipment, and we have 0.23 kilowatt hour per mil on the domestic hot water. So we thought, okay, we are within reach. We need to do a little bit more and we'll get there. Then trying to dive in to understand, the key, the bigger appliances and everything was going on, we found that things were not moving the right way. 1.23 became 1.64 because we find some little inefficiencies such as, us becoming kettle experts where we were trying to trace where the water was coming from, where you get cold water that gets heated to 60-degree hot water through the common system, which then was mixed down with cold water to get back to 43 at the tap, which was then used to put into a kettle and then taken through, electricity back to 80 or 100 degrees, boiling point. So finding, like, connecting with a kitchen consultant to understand how every single one of these equipments were going to be used was really key to then for us to move to the next phase and say, okay, well, this is not really efficient. We can do it this way better. And that part we can use, waste heat and things like that. We've also had the luxury of, with time, having more electricity-based equipment showing up in the market. So being able to keep on reducing that number of gas-led appliances. And that put us to 0.94 kilowatt hour per meal altogether between electricity and hot water. So again, with that deeper understanding, we could get to that higher energy performance, but that could not have been done with, a team that didn't buy into it.
I think at one point I'll just add here that's interesting, again, not to downplay the effort into this, as there was no certification metric. We were inventing the metric. The sort of the one that we showed earlier was really sort of the product of coming through this whole exercise and defending to PHI what we needed. And in that, to say we became kettle experts is a bit of an understatement. We really had to identify literally every piece of equipment in the kitchen, understand its energy inputs, how much water is it heating, how many times a day, to what temperature, from what temperature. So there's a lot of just a lot of legwork there, and really close work with PHI, just to help people understand kind of what's involved in this kind of exercise.
Yeah. So we talked about the electricity consumption of all the kitchen equipment. You can see that we started to touch base on domestic hot water, which is as well a fun subject with Passive House. So where do we start? First of all, if we look at a standard Passive House, I know like everybody's probably familiar with Passive House on this call, but I thought it was a good reminder to show that on a typical household, you need so much heating demand that your domestic hot water take a backup seat as to how much you need. However, with Passive House, you've worked so hard at making your enclosure performing that the domestic hot water, which is the kind of blue-green color here, becomes the biggest end use, right? Because you barely need anything for heating or for cooling, so domestic hot water is the big one. So that is the setting in a residential project. And if you would have asked us earlier on how it would have been on this project, we would have said, well, surely the residential towers with almost 400 beds on each side, that has to be where most of the domestic hot water goes. And then we went and did our calculations and came back saying, wait a second. You know that residential tower that you thought was so big, it's actually only about slightly less than 10,000 liters a day. And if you look at the kitchen, we have about 3 times more daily domestic hot water demand in that kitchen that we have in that towers, purely for showers, leaving alone like extra, additional domestic hot water demand for laundry or washroom or anything else. So with such a high demand and probably a high, like using a big pie of the total energy budget that you're allowed, how do you tackle it? Well, spoiler alert, same thing as what we mentioned before. Still take the same approach. You start by reducing the demand to make it from big to small or smaller as much as you can. Then you recover, right? Whatever waste heat you might have from anywhere, you are trying to reuse it towards that end use. And once you're done with it, you're trying to meet your smaller remaining demand in the most efficient way, right? Which means electrification in our case. So I won't give it away more. I'll let Rufi dive into the technical details.
So how do we actually implement the three steps, as Marine just mentioned, into the project itself? So step one is to reduce the overall domestic hot water demand. So what we did is at the beginning of the project, during the DD stage, we have working quite closely with Perkins and Will in order trying to group all the washrooms as close as together. So in this way, you basically reduce the overall horizontal distribution of domestic hot water piping, which then reduce the associated heat loss. We also try to specify the low flow fixture units, such as low flow shower head and other faucets, to further reduce the domestic hot water demand. Second, Cass, next. Second, we try to recycle the waste heat. UVEC, as presented by Cass previously, it's a very big buildings, and it has 2 buildings, and it has a lot of opportunity to use the waste heat. And the one thing we found is trying to use the waste heat from the shower drain. And you can see, probably most of you are familiar with this product, which is the shower drain heat recovery. And what it does is trying to recover the waste heat from the shower drain to preheat the incoming cold water before it reaches into the shower mixing valve. Next. And the other thing we're trying to recycle the waste is from our massive commercial kitchen, as it has a lot of waste heat from the coolers and the freezers. And in the traditional way, you basically reject this heat, dissipate this heat through the dry cooler. Well, in our case, we actually trying to collect all this waste heat and then dump into a preheat domestic hot water tank. In this way, you will reduce the hot water load further. Next. And after you minimize the domestic hot water load to minimum, then you need to start to think about how to generate the remaining of domestic hot water load. And there's like 2 options currently. One is to use the existing campus-wide district heating system, which is gas-fired. And the second option is to use air source heat pump, the high lift type of air source heat pump. From an engineering point of view, there's a no-brain decision because, compared to gas-fired district heating system, air source heat pump has way higher COP, and usually between 1.5 to 2 or even higher compared to the efficiency of gas, which is about 90%, even you use a very efficient condensing gas boiler. So, the energy input will be significantly lower. And also in BC, as Marie mentioned before, the carbon intensity of gas are much, much higher than the electricity, which is produced from hydro. The only cons from using air source heat pump is it does, the COP does depend on the external air temperature or the ambient air temperature surrounding it. So in order to meet the design temperature of Victoria, which is -8, the option has been quite limited, which we will touch base later. But the first, I guess, just trying to address actually the decision on this point to make the choice between the existing campus-wide district heating or to use air source heat pump has been quite challenging, has been quite back and forth. And Cass now is going to explain why.
Yeah, so as we just mentioned previously, the university really, their driver and their entry point into high efficiency was really driven by carbon. That's kind of their at an institutional level, that's their value set, which is noble, which is great, and we support. However, not that many years ago, they had invested roughly $20 million into upgrading their district energy system in anticipation of this project coming online, so through their master planning. So they had all of this capacity in their district energy system that was, built for this project. And then we came along and said, hey, maybe you don't want to do that. Maybe you want to leave that cost that's sunk in there for a different use or for something else, but we're basically telling them that that's not really how you want to go in the future. And interestingly, I think the university is now starting to think about their whole energy system and their energy future, which I think is something we'll start to see more of from institutions coming down the pipe. So really what we saw here is the university did decide to go toward an air source heat pump at an increased capital cost. Basically, it's very cheap to plug into the existing DES because they already sunk the capital cost in at the plant. They got an 88% annual greenhouse gas or carbon reduction. However, it did come with an operational increase. If you remember at the beginning, we talked about electricity in BC is about 3 times the cost of gas, roughly. So although it's a higher efficiency, you ended up with an increase, operational cost per year, increased capital cost. But the university really stood by their value set and said, no, that's the way we want to go, and that's the future. Another thing, I don't know if Rufi mentioned, she will, coming up, is just around being at the bleeding edge of the market with some of these products and some of the complications that brought in.
So after we talk a lot about how to incorporate of these innovative design to reduce the overall energy demand and space heating demand, like Kaz and Maria and I thought, oh, finally we can perhaps sit down and relax for a bit. But actually it's really far away from to be relaxed. And because I think one thing I've learned from working on this project is working on a large-scale passive house projects, the design process is never linear. It's always going through little bit twists and turns. And I guess one of the challenges we found for doing this project is the North American market is still developing their large-scale, high-efficient mechanical equipment, which I will use 3 examples to demonstrate. The first one I want to talk about is the journey of specifying the kitchen heat recovery. As Maria and I mentioned before, it's very key to keep the space heating demand for the kitchen ventilation to a limit, as we do need to provide a lot of kitchen exhaust flow rates, even after all the technology we have to use trying to reduce it. So from the beginning of the project, we have always been using hot and heat recovery unit, which we also use for some other projects before. However, I think it was around 50% CD, and I remember clearly on the day when we tried to submit our progress to Perkins & Will, I received a call from Horton and basically told me they no longer produce the hot and heat recovery unit. So obviously I was very frustrated, but immediately, we jumped in and we tried to find an alternative supplier. And to our, shockingly, we can't find a second supply in North American market to produce the equivalent of hot and heat recovery unit. So we talked to a lot of suppliers and, manufacturers, and then finally found that this guy basically lives in Ontario, and they actually does bespoke heat recovery unit, use plate heat exchanger. So we immediately flew there and trying to check out this unit, and what we found is basically it was designed and basically built by this 70-year-old man who you can see in the second photo, between me and my boss, and he basically built this product at his backyard, which also we are really, admire his product, but, due to the warranty and all the other issues, we can't really specify that product. So that option is dead. And what makes us more frustrated is we actually found our product exists in Europe. Horton actually make exactly the product we want to use for our project, but it only exists in Europe, not in North America, due to the challenges of to comply with MT TFI 96 and also other Canadian standard. So it's impossible to import that product into North America. And we also look at the earth tube option because we know, it's a very cost-effective way to preheat the incoming cold air. However, as the design process has already been progressed through 50% of CD, and introduce earth tube at this stage will have quite impact on the overall space planning. So the option is also be removed. So finally, what we come up for the project is trying to use a very advanced version of ecology unit, which is called the Puller Stop unit from Horton. So this product basically incorporates a lot of layers of sophisticated layer of filters in order to remove completely the grease from the kitchen exhaust. So after the layers of filter, and we can be confident to recover the heat from the kitchen exhaust through the run around coil to preheat the incoming cold air. So finally, our journey reaches the end is to specify this product. So,
actually, there's a point, Rufi, if I can, just to echo on the Halton, the point about the Halton product being available in Europe and it couldn't be imported, or it was very, very complicated to import. We had a similar conversation around heat pump dryers at a commercial scale. Just important to note, or something like be relevant to people. So we could find residential heat pump dryers, that was no problem, but we needed to have something more durable for the amount of use they'd have. And so in conversations with suppliers, off the record, they basically communicated that for them to get their products certified through CSA in Canada, or the appropriate groups in Canada, it was a very, very difficult argument to make from a business perspective, the cost to do it versus like a 20-year payback on what they expected to sell. So that was sort of another frustrating point we ran into, and there's a whole bit about dryers that's not in this presentation that we could talk about another time.
Next, yeah. So the other thing, as mentioned before, like we want to specify large-scale air source heat pump, and it has also been challenging because the availability of the suppliers. So ideally, what I would like to specify is a CO2 air source heat pump, because we know it has zero global warming potential, which is really perfect. However, the only CO2 product we found is Sandon product, and the output is only about 4.5 kilowatts. So if I have to use our product, I need to specify about 60 products to just one building, the one with the commercial kitchen. So that's not feasible. So then we look into the large scale air source heat pump, and the majority of large air source heat pump can only operate to 4 degrees, which means you need a backup to the operation when the external weather is below 4 degrees. So eventually we found this product from Comact, which is CXV, and this product can operate up to -8 degrees, which is the design temperature in Victoria. However, it is quite small compared to the large-scale units. So for building one, we still have to specify about 15 of them to the project, but that's the best what we can do. And the last one is about heat recovery units, which is also a very interesting process when specify the product. So I think most of you probably know, like Rigor has been less dominant passive house certified large-scale heat recovery unit supplier in North American market for a very long time. And so we have been using them to form the design, space configuration, etc. from the very beginning. So when we issued our tender and when we were just preparing our addendum to the tenders, suddenly we got a call from the second supplier, which is what you can see is called Flackwood. And they basically work along with Train, and then they finally get the certification, or they're in the process to get the passive house certification for their large scale units. So they were really keen to join. And in order to encourage a fair competition, to allow more supplies to be included for the client's benefit, so we have included them into our tender addendum. And after we issued the tender, and now we're just approaching to the end of IFC, we actually got third call from the third supply, which is called Multicross. And they basically now told us they are also entering into the North American market, trying to, join the selling the large-scale passive house certified heat recovery units. So it is really good to see like there's now more suppliers trying to, join the North American market. And I think the next project will be confident we can have multiple supplies included in our specification and encourage a more fair and competitive price for the client. So that was just another story to tell, like for this project, in terms how to find an alternative supplier and how to find, the right supplies for the project, which Maria and Kaz will talk a bit more in the next sector.
Yeah, so it was interesting getting these calls and understanding that more and more products were coming on the market, but it's not as simple as saying, oh great, you've got a new product, let's use it with all of the strict criteria we're trying to meet. And Maureen is sitting there with a 1,000 different levers in front of her trying to balance them all. So just swapping out units is difficult. And that's something we wanted to get into. This is a new section we haven't really presented before, but something we've been grappling with more recently through the tender process and sort of really the tail end of design. So just sort of we'll talk about three primary items here. So late in the design process, new issues emerge, or we came across new things. One was spending our design buffer. So the whole time we always were trying to tend under 15. So we knew in case it wasn't available or for whatever reason, we have a little bit of buffer, which is just good practice, particularly on something of this complexity. And then an approach, sort of lessons learned from sort of a value engineering or value analysis versus energy performance perspective. We did go through a value engineering process on this, and there were a lot of different conversations that we wouldn't maybe normally have. And then substitutions, going back to the equipment, and we'll have a different example. Two examples we'll kind of walk through quickly. We'll try and walk through quickly. Wrap this up in about 9 minutes or so to leave some 20 minutes-ish for Q&A.
Okay, so diving into this quickly. So as Kaz mentioned, we're trying to juggle all these levers, all these plates in the air while every single discipline is busy like working to a certain performance target. And so we, right after tender, we looked at it again and we're like, okay, actually, we kept a good buffer, like not a lot of things have come and, ate at it bit after bit. So we were like, okay, we're at 13.3 as a combined average of the Podium and the Tower models. At this point, getting closer to getting to site, surely we can start using a little bit of a buffer. So then we looked at a few different measures to try to get back, trying to get closer to 15. So not reaching 15, still leaving a little bit of a buffer because we know how construction goes and things might not go exactly according to plan on site, but at least bringing back a few measures for, purely as a cost saving to say, okay, guys, we don't need to maintain, we did a good job. We had ups and downs. They can tell you about this. We were above and under and above and under. But the final point was, okay, we have a little bit to spend. So let's make the project a little bit less expensive and bring in a few measures. And what you can see is that we finished at 14.5, which is like the bottom right of the table after testing a few and deciding on the exact combination, which obviously was looking at the impact of energy as well as cost. So great, we're there. This is where we're supposed to be. However, now that the tenders have come back, we're looking at a whole list of VE. And what is different from typical projects is that performance has to be maintained. There is no way around it. It simply has to be. So what does it look like when you start diving into it? Honestly, the picture on the left is like a tenth of the entire list that Perkins and Will has compiled together through every consultant, where we looked at like, I don't know how many, actually Cass, you can say how many VE options. Too many.
Very, 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 very many. Yeah.
Yeah, and out of all of that, we directly discarded some that couldn't work for the energy or cost, size if the savings were negligible, and extracted the key ones to then, again, I'm not going to say how many iterations we went through into the model, but you can see on the right all the key measures that have an energy impact then being logged into all the models to try to deliver answers. And what we found is that that need to maintain performance makes the project different from a typical project. And we found that we've had measures that have worked really well and some others that work a little bit less well.
We'll just talk about a couple examples here. It was interesting too, because we did the CM on board and we had trades actually on board as we were going through VE. So we were getting feedback from all these different groups, and some suggestions were great and some were not great. And it was really interesting because some of the trades didn't really know what they could touch or couldn't touch. So we had some interesting dialogues there. One thing we did look at, we were originally looking at the client's technical guidelines want an inverted roof. We couldn't have a proper inverted roof because of the buoyancy of the amount of insulation on the roof. It would just require so much ballast. It was getting ridiculous. So we had sort of a split inverted roof with so it's somewhat conventional and then still a protected membrane on top. There was value savings to go down to a more conventional roof. And that was something we could accommodate. We could make that switch and achieve the thermal performance. So great, that worked out really well. Another one we looked at was, so there are two options here we looked at. One was reducing the below slab insulation. That was, if anyone caught it, was on a previous slide in terms of spending our passive house buffers. We reduced the below slab insulation, and then a trade brought forward the option to move to a different type of insulation from an extruded to an expanded XPS. But again, it was just an interesting point where they didn't really understand that to get an XPS, they would have the same insulation value per inch would put us back, it would produce no savings. So it was an interesting conversation around people understanding the thermal performance metrics and how that relates to cost. And some things we just couldn't do, and some we really could accommodate. More complex though was this.
Yeah, one final example on the substitution was on the curtain wall. We were originally given, sorry, not V, but a product substitution saying, oh, this curtain wall is going to be replaced by that one, and that one is still a PHI certified product. So the entire team were like, yeah, okay, sounds good, sounds like exactly what we're trying to do. And diving into the detail to say, well, we still need to check that the performance is maintained, led us to like down the deep end, right? And the fact is, a certified product is not the same as the spec or like the performance target that you have yourself set on your building for your overall building to work, right? Because Passive House is not prescriptive, so we get to be the chef and with our own recipe and decide where we want to spend our energy budget. And the three key impact, without diving into the detail on a window type product, is the glazing, the frame, and the spacers. And you can see at the bottom the basis of design that we were working with, and that was for the tender documents. And then the alternative was like, yeah, we can do the same, we do better, it's all good. And more or less trying to speak the same language and looking at, having like apples with apples comparison, we had to dive into reading performance specification and test data in German when I do not yet maybe speak German, where we start understanding that some values were, in a certain way. And so we came back to the like for like comparison, which was like, oh, actually you're slightly higher on this one, but maybe you're slightly better on the next one. And then that was purely for the fixed part of the curtain wall. And then we're we added like additional levers and moving pieces through the glass carriers that are typically required with curtain wall. And then we have operable vents within the curtain wall, which again was the glass carriers were worse, but the operable vents were better, but the doors were worse. And we all had to like go deep into everything to say, okay, when you say it performs this way, do you actually mean it? And then log it all into the model to then at the last minute say, whew, okay, I think all in all, the model barely sways because all the negatives are balanced by the positive. So yes, that was worth it. Let's go with it.
It was interesting though, these people spoke the language of passive really well, so we were able to connect with their technical team and get this really detailed review. And Maureen obviously did a ton of work laying out exactly what we need and talking about how many screws at what spacing and all these things. We did have another interesting tender substitution on fiberglass windows. So we specified a particular fiberglass window with a particular installation and a particular performance, and there are a number of people who make these. So a few people came with substitutions saying, no, the installation's the same, our performance value is the same, everything's the same. And again, when we dug into it, it was different because some of these folks, some of these groups didn't really speak the language of thermal performance as fluently. So while they made claims, let's say, that things were similar, when we did start to dig into it, we realized that they weren't, or the installation details were significantly different and would have a significantly higher thermal bridge at the connection. And so it was interesting to, with these groups, what we weren't able to accept some of them as alternates, but we were really trying to provide them with information so that next time around, they could get the modeling done on their product, they could provide us the values, and they could actually come to the table. So we would just love to see more and more players in this market space providing the technical details around all these components so that we can, with confidence, take them in and use them in the model. I think the take-home message here is, you really have to cross your T's, dot your I's, and check what people are saying, and also just understand that people have some fluency or understand the conversation you're having around performance. So with that, just to share a couple final thoughts really quickly, so we leave some time for questions. One thing we did struggle with, or not struggle with, that's the wrong term, is have back and forth with the university late in the game. We did go through a V-cycle. There are some expensive systems in this, or novel systems in this building. And the university was really interested in carbon. And we had a lot of conversations around sort of, look, if we go all electric, we can cut our carbon emissions in BC by, let's say, 90%. So the investment in a really high performance building, it's not doesn't appear to be a great return on investment. So we started to talk around the idea of, well, why do high performance buildings matter on a high efficiency grid? Being able to get that small GHG savings sorry, there's an ambulance going by me. So we started talking a lot about preparing for the future, reducing demand on the grid, reducing the need to upgrade their mains into campus, and preparing for the future, really getting in line with the STEP code and saying, we want to prepare for the renewable future and limit the amount of renewables you may need in the future. Really talking about that net zero ready building. Another question we've received a lot through the process is, every time we speak about this, is kind of, what is the cost premium for this? And it's really difficult to say, but one study we did do with BTY is that 50% construction documents the university requested, so this building is pursuing passive house certification as well as LEED v4 gold. So they said, well, what would be our cost savings if we, from this design, dialed it back to just a LEED gold building and remove the passive house requirement? So it's not really cooking it from the ground up. And so we reduced the installation, did all the changes we thought would make sense, running it through the passive house model, and we came across about a 5% premium. Is that premium? That's just for this project. We have a large commercial kitchen that may be different for a traditional MERB project without sort of that high intensity specialty use. And then a couple of other lessons learned from UVic and the consultant team. The university has found pursuing this process really valuable, just in terms of the institutional learning that's taken place. So they now have an understanding of high efficiency buildings that's much more robust than they previously did, and helps provide guidance. Like, they've walked through this, so now they understand really what they're asking for in future RFPs. Also, their staff members, so their internal shops groups, their mechanical teams, they're subject matter experts. So they've reviewed air source heat pumps. They've talked about these things in the maintenance and life cycle. So that better equips them for these conversations in the future. The really big win for them was increasing about 600. I think it's about 623 beds, but a net decrease of greenhouse gas emissions. So they're growing their campus and moving the dial in the right direction. And one we didn't really talk about a lot, but in part of the kitchen, is by switching that to all electric on our electric light carbon grid, is they avoid all that lock-in. So if they built a gas kitchen for the next 60, 80 years, however that kitchen, whatever the lifetime that kitchen is, they're just continually burning all of that gas. So when we talked about switching that kitchen equipment, there's an 88%, I think it was, reduction in greenhouse gas emissions. That was for the entire building, not just for that kitchen. So it was just a tremendous impact. So with that, I mean, we've covered a wide range of material, but I'd love to open up to questions. Sorry, Chris, I think you're muted.
Yeah.
There wasn't any questions in the chat, other than I got a bunch of private ones on AIBC credits and PHI credits, which I'll deal with. And we typically have been submitting them to the appropriate organizations, getting the certificates and sending them out, just for everyone's information. If anybody has any questions, I just suggest, we're a relatively small group, we're a smaller group now. Kevin was asking a simple one. The presentation, this has been recorded, so it will be on YouTube. We typically try and send out a survey and a link to YouTube in a couple of days once this is completed, just so you're aware on that. And then if the presenters are willing, they can provide me with a PDF, and I can include that in that send out. It's their content, so it's up to them. I had a couple of questions that I can answer, and I know that I mean, we've seen this one before, and everyone is always reluctant in the kitchens, and that I feel like a big battle for you guys was switching from that gas kitchen to electric, and all those chefs saying, I can't cook without gas. Was it predominantly induction, and did you have to, like, how did that work, or how did that get through within that kitchen staff? I mean, just the ground level cooks.
So yeah, the conversation, it was an interesting conversation, because the marketplace for kitchen equipment was evolving very rapidly as we were going through this. So at first there was they were saying, well, we have all these pans, we need specialty things, and we're just sort of ate it in bites. And we're like, well, you're going to get all new stuff anyway. Let's say, like, that's part of the project. That's sort of insignificant. We can buy you all new stuff. And it was really taking them places like, hey, this restaurant in Victoria uses induction cooking, and getting them on board with the ideas of internal heat gain. And I think honestly, a lot of it was the user groups seeing the excitement of the people around them when they announced it was going to be Passive House, and how much interest there was. And then they started to say, hey, this is I guess this is cool. Like, let's lean into it. And then we started to go to these things. They went to Toronto and with our food service consultant, and went to a showroom that had all of these things. And they just really, once they saw it and said, oh, we demystified all these things, I guess is really what it is, and just made them aware of how good some of these products are. And there were a few straggling products. One in particular was the deep fryer. Their thought was, there's just not an electric deep fryer that has the heating time that we need to actually run an efficient food service operation. But then late into CDs, a new item came on the market that did meet their cycle time. So it was a whole bunch of factors, but I honestly attribute it to really just two things: getting people excited, or people getting excited, and then really slow, methodical education.
Makes sense.
Something that helped.
Go ahead, Marie.
I was just going to say, one thing that helped as well is that the university themselves had really bought into it, right? With the whole greenhouse gas emission reduction targets they had for the campus. So in a way, I feel like even if we came from very different background, both the university leadership as well as the design team were driving in the same direction, which at some point the kitchen staff, you know, got excited and went on board, right? It was not like the fact that the client was so dedicated to it, for me, changed a lot of our fights, right?
For sure. The other, I was, Ian, if you're there, Ian Douglas, do you want to answer your question directly so I don't butcher it in the conversation? He's not there. Quickly, I can ask it. Essentially, his question was just speaking a little bit more on the use of heat recovery with the grease-laden air, specifically to the regulatory hurdles, and is how big a difference is the Canadian market for high efficiency equipment from Europe's market?
Sure. So for the kitchen heat recovery equipment, I mean, it's still like, it's quite innovative, and what we're trying to do is to use the Horton, the puller stop unit, which is a very like cutting edge models from Horton even. So what they did is they have layers of filters, including carbon filters and electronic precipitators. So all these basically the intent is trying to completely remove the grease from the kitchen exhaust. Obviously it requires regular maintenance to these filters to make sure, you know, actually the efficiency of these filters can operate constantly or consistently throughout whole operation. So based on these filters, then we can be confident, like, you know, the grease from the kitchen exhaust can be removed, and then that will not clogged and the runaround coils, which we will install on the upstream of the puller stop unit. And we are still need to, obviously, once the unit is installed, we require inspection and to make sure like they comply with FDA 96. And they still need to require a lot of filter testing requirements throughout the construction stage. So yeah, like once it's installed and in operation, then we probably can feedback more about how it operates. And, you know, it's the first time of a lot of things. So we're still looking forward to see how actually the outcome it will become. And I guess the second question is like how big a difference is the Canadian market compared to the European market. So I guess just use the example of kitchen heat recovery equipment. As you can see, like we found that product from Horton in Europe, and I even trying to call their you know, headquarters, which is located in UK and in France. And unfortunately, it's difficult to reach out, but the product does exist, and so examples and which they use for multiple projects. And also Marine has introduced a lot of kitchen heater recovery products through Passive House Institute. However, these products are heavily used in Europe, but quite small scale, which is not very applicable to our project. But also, I think the key thing in terms of the regulatory hurdles are, it seems like the manufacturer are very reluctant to testing the products to comply with an FDA 96 and also other Canadian guidelines. It's just like the amount of process or the cost associated with it makes them really reluctant and put them off to import the product to North American market. What we would like to see is perhaps now, because, you know, UVEX set up example for doing Passive House certified commercial kitchen, and there will be more and more projects requires to achieve the Passive House certified commercial kitchen, that perhaps can encourage, you know, the suppliers and manufacturers to explore more ways to import these products.
Perfect, thank you. I would say I think I'll just read out the next question, which it's actually my question. I believe all the exterior shading is fixed on that project. Did you look into any retractable exchanging or any mechanical movement in any of the exterior shading?
We talked about it really briefly in house, but it died on the cutting room floor pretty quickly, largely from the operational concerns on the client end around the maintenance of that, particularly around the west face. You know, that's a great face where the use of the building, the room in building 1 on the west face is this sort of multi-purpose ballroom kind of thing where they wanted floor to ceiling glazing, and then we're more or less covering it in shading. So we looked at doing it there, but it was a difficult one to climb, particularly at that point. We were facing budget challenges as well, and it just feels exotic. It's a difficult hill to climb.
Yeah, I think just trying to add to Kaz, like because dorm, like each dorm only has 1 person. Also, like, you know, we need to, you know, consider the overheating for the dorms, but because it's such a low occupancy density and a low internal heat gain compared to the podium, so we would like to spend the money on the solar shading more focused on the podium level because it requires more, you know, extensive solar shading to reduce the overall internal heat gain. So I think it's good to use retractable, but it's not necessary for the dorm room windows.
And we're also working with much thicker walls as well. So technically, even without shading, the window itself, especially in the dorms, right? The windows themselves have already a deep enough reveal that does cut some of your solar gain. So trying to keep it simple for the installation part of it.
That's perfect. The next one is, I think it's a good one too, is from the local building department of the municipality with regard to, I mean, you've got a lot of unique systems going in to achieve this. Have you had any pushback from those systems or approaches from the municipality and the building department? Or have they been, Victoria, been fairly receptive?
Yeah, so we're actually in Saanich is our municipality. Something I learned more about in this project is Victoria is the whole area, but it's many different cities in there. And they've been really supportive. We haven't had, I don't think we've had any comments related to any of these novel systems.
I think one thing perhaps we're being pushed back is we're trying to use AAVs for the vent and the plumbing venting system. So we did contact them and trying to see the possibility of incorporating them because it's quite common for passive house buildings, but basically they said no. And then we did all the, like Maureen did all the sensitivity analysis, and it seems like the impact is not that significant. Hence, we didn't include for the final design.
Yes, so the AAVs are air admittance valve, which are trying to more or less reduce the heat losses that you have with the vented sol pipes, right? If they're fully open to the outside, you get a bit more. So that has always been a challenge in Canada, and I think that the only one I know of is one around here in Hamilton, where they've managed to push through an alternative through a lot of work again, like a lot of reporting and, you know, discussing with the authorities. So it wasn't an easy one, but it has passed, so there is precedent now.
But I think too the return on investment in terms of energy to pass that one, we weren't seeing tremendous energy savings.
Perfect. I think this is probably the time for, we're almost done, so I'll go one more question. Hopefully it's not too long of a one. In regards to the, I assume this is the construction RFP and the process for one, were the targets for lead and the passive set in the RFP, or did you subsequently establish those? Was it, how did you get to your contractor?
I'll answer it from two perspectives. I guess there's the RFP to which we responded, and that one established the target as LEED Gold. That was the institutional standard at that time. And then early on in the concept phase, or the early on in schematic design, their steering committee just put out new goals, and they're like, hey, look, this is a big project. This is by many-fold, by couple-fold, the largest project UVic's ever pursued. So we want to do something right. So they asked us to explore what would beyond LEED Gold look like. And that really opened the gate. And we did a very extensive series of workshops with them around sustainability and what different metrics are out there, what are their goals, what dovetails with their goals. Carbon came on, they became really interested in Passive House as we learned more about it. So that actually came to the project through the process, and then that was part of the RFP for CMs and that kind of stuff. So we started as Lead Gold, and really just through a series of workshops and understanding and really educating the client of the benefits of these things. And some of the benefits from Passive House, like the student housing people were really interested in the comfort, indoor comfort, because they have students from all over the world. They have students coming in from the Caribbean and people from the North, and they're trying to provide comfort. And realistically, they're dealing with complaints. And if they can reduce that, great. And we're like, no condensation on the windows. And they're like, amazing, because their 1960s housing stock is probably pretty sweaty on the inside sometimes. So I think all these factors really weighed in. And one thing I really would credit the client through and through is really taking the time to learn about this. There were a particular handful of individuals on their building committee or their executive committee who, one from the student housing group is an engineer by training, and they really leaned into it and learned about it. And now when we have conversations, that's at a pretty high level.
Perfect. I like this. This is the last question. When is this one scheduled for completion? When do we get the final tour? The ribbon.
So we're just ramping up for IFCs. They're digging a hole basically now. So construction has started. We already led a couple early works packages to do some demo. The two of the buildings on site are demoed. We're opening the first one. I think it's supposed to be fall 2022, and the next one will follow by about a year.
Amazing. That pretty much hits our time bang on. So I really enjoyed that. I wanted to thank Kaz, Rufi, and Marine. That was awesome. I appreciate there was a lot more information. I know I've seen that presentation a couple of times now, and there was a lot more depth there. So I thank you for that. I guess with that, we will sign off, unless anyone else has any final thoughts. Awesome. All right. Thanks guys.
Everyone.
Enjoy your evening.
Thank you.
See you next time.
Thank you, guys.
Thanks, guys.
Bye.